Hello everyone. For this tutorial video, I'd like to discuss directional derivatives, or the rate of change of a multivariable function with reference to a specific vector direction rather than an x or y variable. The formal exact definition of the directional derivative is function of x plus a times h, comma, y plus b times h, minus function of x comma y all over h as h approaches 0. Although this is the formal definition, it can be hard to use, so we can get an easier formula by doing function of x sub 0 plus a times z, comma y sub 0 plus b times z. We now take the derivative of this using the definition of a single variable derivative, because we have everything in terms of z, as x sub 0, y sub 0, a and b are all constants. So we actually have a single variable function, even if it may not look like it at first. The derivative at 0 would simply be plugging in 0 in the definition of the derivative for z. And we can see, fortunately for us, that with some foresight, the derivative at z equals 0 can be rewritten as the limit at point h minus the limit at point 0 all over h as h approaches 0. And this is beginning to look like the exact definition of the directional derivative we saw earlier. So now, since we know z is a function of x and y at the same time, g of z equals f of x comma y, where x is x sub 0 plus a times z and y is y sub 0 plus b times z. We can compute the derivative of this using the chain rule, and seeing that a and b are a change in x relative to z and change in y relative to z exactly. So we have the simplified formula using the notation for partial derivatives with the subscript of the variable you are taking the partial derivative of. So now we take the derivative of g at 0 by rewriting the x and y into x subscript 0 and y subscript 0 in the partial derivatives, and we conclude that we can generalize this into directional derivative of a function equals partial derivative of one variable times the change in the variable relative to the output z, and we add that and get the same result for the second variable. If we have a function with 3 inputs instead, we would simply add the partial derivative of the third variable times the change of the third variable over the change in the output w. So if we are given a specific direction and a specific function, we can compute the directional derivative by first taking the unit vector, or vector with length 1, calculate its components using trigonometry, and then simply multiply the x component of the unit vector by the partial derivative with respect to x, and the y component of the vector with the partial derivative with respect to y, and then add them as indicated by the general formula for the directional derivative. So after we do the arithmetic to simplify our work, we see that it is 5 times square root of 3 minus 1 all over 2 as our exact value for the directional derivative. Before we head on to applications of multivariable derivatives, I would first like to explain an even more simpler and compact formula for the directional derivative. In particular, if we choose a multivariable function to have 3 variable inputs, we see by the formula we found earlier, this equals the partial derivative with respect to one variable times the change of variable over the change and the output. And this is true for all the variables individually, and then we add these. And we can see, by how we know vector multiplication works, that this is a dot product, where one vector is the partial derivative of each variable, and the other vector is the components of the rate of change of each variable over the change in output, or essentially the components of the vector that gives the direction. So we denote the vector that represents the partial derivatives with an upside down delta, and this is called the gradient vector, or gradient for short, as gradient is a specialized term meaning a rate of change or slope. So we conclude that the directional derivative in its most simplest looking form is the gradient vector times the vector that gives us the direction, where this multiplication is a dot product specifically and not a cross product, because it is important to remember that vectors multiply out in two distinct ways, which is not true for normal numbers or scalars. Now that we have figured out how to express different types of multivariable derivatives, we can explain why they are useful or applications of them in the next videos. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.